All right, so in this section, like I said, we're going to take a look at displaying quantitative graphs specifically. After this section, you will be able to construct and interpret dot plots, stem plots, and histograms. Just keep in mind, anytime you see the word interpret, that means to interpret in context of the problem. So remember that statistics is just as much as a math class as it is an English class, and you're going to want to be able to interpret your results so that anybody walking down the street can read your sentences and know exactly what your graph is displaying. You're going to be able to describe the shape of a distribution, compare distributions, and use histograms wisely. All right, so in the last section, we talked about displaying categorical data. How did we display categorical data in the last section? We took a look at bar charts. Remember from the Forbes article that bar charts are different from histograms, so make sure you've read that article and understand the difference. And we also used pie charts. Remember that pie charts are always in terms of percentages, and they are always you must have a 100% or the whole thing for a pie graph or a pie chart. So how exactly are we going to display quantitative data? Well, there's 4 different ways we can do this. One is through a dot plot, which is shown here. One is through a histogram, which is shown over here. The third is through a stem plot, which hopefully you have done before. Okay, and the last one is through a box plot, okay, which we'll be going over later and showing you specifically in a later section how to look at a box plot. So there are 4 ways to display quantitative data, and specifically I had said earlier that you need to really understand the difference between categorical and quantitative data so that you know which type of graph to create when displaying your data and explaining the information from your data. All right, so first let's take a look at a dot plot. It's one of the simplest graphs to construct and interpret is a dot plot. It's very easy to read, it's very easy to understand, and it displays the data very simply. Each data value is shown as a dot above its location on a number line. So how do we make a dot plot? First, you're going to draw a horizontal axis, a number line, and label it with the variable name. So 1, make sure you label it with the variable and give it a scale. So 2 is what I just said, scale the axis from the minimum to the maximum value. Make a dot above the location on the horizontal axis corresponding to each data value. All right, so here's just some quick data. Here's the number of goals scored per game by the 2004 U.S. women's soccer team. So for example, the first game they scored 3 points, second game they scored 0, third game they scored 2, fourth game they scored 7. What does the dot plot of that look like? Well, first of all, the smallest number of goals was 0. The largest number of goals was 8. So we drew an horizontal axis and scaled it from the minimum 0 to 8 the maximum. We labeled it, that's really important, the number of goals scored so your reader knows exactly what they're looking at, and then each dot we just went through. So at 3 we put a dot at 3. At 2, we put a dot at 2. So it's very easy to see, okay, it looks like most of the games they scored 1, 2, or 3 points. The least amount of points they scored was 0. The highest amount of points they scored was 8. So it displays the data very clearly. You can read it very quickly and get a quick summary of what your data looks like from a dot plot. So why do we want to make a dot plot? What information does that give us? So why would I choose to make a dot plot over a histogram, box plot, or stem plot? Because each type of graph has an advantage to displaying the data and what it shows over another graph. First of all, it's very much less abstract. Okay, it's very easy to read. A common person can look at it and say, okay, there are 4 black cobra snakes. It's easy to see the distribution of values, the heights. As long as your dots are all the same size, it's very easy to see exactly how the data is distributed. For example, here among the types of snakes, okay, at the zoo there was the most rattlesnakes and green cobras. It's easy to see individual values. I can very quickly look at this and say there are exactly 4 black cobra snakes at the zoo. So what is the purpose overall of making graphs? So the goal of making graphs is to see what the distribution looks like. All right, there's going to be a few specific things that we want to find out or specifically look at from our distributions. Next, we'll examine exactly what the graph tells us about that distribution. Okay, so how do we go about examining the distribution of a quantitative variable? The purpose of a graph is to help us understand the data. Remember that statistics is the science of data, and we want to be able to manipulate the data so it tells a story, and we need to be able to clearly communicate that story to somebody else. So after you make a graph of your data, you always want to ask the question, what exactly do I see from that graph? So this slide we're going to determine how to examine the distribution of a quantitative variable. All right, so specifically in statistics, oftentimes directions will just say to interpret the graph, describe the distribution. So you have to understand what that means even though the directions aren't necessarily given. So if a set of directions says, examine the distribution of a quantitative variable or describe the distribution, these are the 4 steps that you're going to need to follow. First of all, in any graph, we're going to look at the general overall pattern and we're going to look for striking departures from that pattern. Are there any values that are too high? Any values that are too low? Are there 2 medians? Are there 2 averages? Is there a lot of data points at one specific value? So when the directions say describe the overall pattern of a distribution, this is what we're looking for. Number 1, we want to look at the shape of the distribution. Number 2, we're going to look for outliers. Is there any points that are much higher or much lower than the rest of the graph? Where is the center of the distribution? And what is the spread? Is there a lot of variability? Is it very far spread apart, or is it very close together with not much variability? So when you see the word describe the distribution, you're going to have to understand, you have to explain what the shape, the outliers, the center, and the spread is. So what's an easy way to remember that? Okay, an easy way to remember that is your socks. So just like in the morning when you're getting ready for school, you don't want to forget your socks in the winter. When we're taking a look at distributions, we don't want to forget our socks. So S is we're describing the shape, O is the outliers, C is the Okay, so now you have the directions, describe the distribution. What exactly does that mean? Please remember that anytime it says describe the distribution, you must do socks. Shape, outliers, center, and spread. Even though it's not explicitly stated in the directions, you have to understand that that's what the question is asking you. All right, so the table below and dot plot displays the Environmental Protection Program Agency's estimates of highway gas mileage in miles per gallon for a sample of 24 model year 2009 mid-size cars. If you think about this, this is the example that we used in the previous section. So here's our model of cars. Okay, here's our dot plot that represents our miles per gallon. So remember that in this case, we labeled the horizontal axis. We have the lowest value, the highest value, and then each of the dots represents one of the miles per gallon. So if we say describe the distribution, we're going to take a look at the shape, the center, and the spread, and then we want to ask ourselves, are there any outliers? So let's just take a minute to look at the next few slides to examine what all of this means and what you're expected to explain whenever you're asked to describe the distribution. Another thing that you want to make sure you do is make sure you put it in context, okay? So when someone reads this question and you're talking about the shape of the graph, they should know somewhere that you're talking about the shape of a graph and you're discussing the miles per gallon for a sample of year 2009 mid-size cars. Okay, so what does it mean when we're asked to describe the shape? So you might remember from your summer assignment or your beginning of the school year assignment that when we're asked to describe the shape, we're looking for a distribution's shape. We want to concentrate on the main features, all right? Basically what we're looking for is rough symmetry or clear skewness. No graph is ever going to be perfectly symmetrical, or it might not be highly skewed one direction or the other. Is it roughly symmetrical? All right, so what are the three basic shapes we're going to be looking for? Number one is roughly symmetric. So a distribution is roughly symmetric if the right and left sides of the graph are approximately mirror images of each other. Please make sure you never just say symmetric. It is approximately symmetric, roughly symmetric, and this is where you can fold the graph in half and it's the exact same on both sides. It's not going to be perfectly, but it is very, very close. Okay? So this is a graph of a roughly symmetric. Okay, if we were rolling the dice, what numbers came up? Okay, if I sort of fold this graph in half right here, it's about the same on both sides. Okay, and we'll be talking about this later, but it's sort of a nice bell-shaped curve. Okay, a distribution is skewed to the right or right skewed if the right side of the graph containing the right half of the observations is much longer than the left side. I think of this as a tail. The tail of the graph is on the right, so it's right skewed. So here's our dog right here. His tail is on the right hand side. So if there's a long tail of values on the right hand side, it's skewed to the right. If it's skewed to the left-hand side of the graph is much longer than the right-hand side. Think of a dog wagging its tail. Its tail is on the left-hand side, so it's skewed to the left. So right here, this would be an example of a left-hand skewed graph. Notice the left tail is over here. Okay, think of a dog wagging its tail over here. Okay, this right here is skewed to the right. Okay, so if you're going to kind of draw a curve over it, right here, here's where your tail is. Okay, the dog is wagging the tail on the right-hand side, so it's skewed to the right. Roughly symmetric, never perfectly. Draw a little curve, it's sort of skewed to the left or skewed to the right. All right, so what if it doesn't look like any of the normal three? So the three on the previous slide were the graphs that you will see most often. Okay, so for example, this one right here are rolls of our dice. Okay, somebody rolled a dice and we just took a look at what numbers came up when they rolled the dice. Specifically, I believe this is the sum of 2 die. Okay, this graph is called unimodal. This is what you will see most often in this course. What does unimodal mean? Unimodal means there's really only one peak in the middle, okay? So, or maybe two that are very close, but there's really only one peak in the graph. If I were to draw over it, I'm really going to peak once, okay? So unimodal is one peak. This is the peak right here. Okay, so for example, this is rolls of 100 dice and we're adding the sum of the die. Okay, so that's unimodal. We would say it's approximately symmetric and unimodal. So both of those descriptions. Okay, so what does it mean if it's bimodal? Bimodal means there are two clear peaks, okay? More than two mean it's multimodal. So if we look at this, if we're going to kind of draw a curve, our curve would go up here, so there'd be one peak, and then up here, and there'd be a second peak. Okay, so this is called bimodal. So there's two modes or two things that are the most. One right here and one right here. Now keep in mind that you can have a bimodal approximately symmetric graph. Okay, so if you have two peaks that are kind of the same, that's why we have to be very specific when we say unimodal and symmetric. Okay? Another type of graph is uniform. So think of uniform. What does uniform mean? It means everything's the same. So the bars are all about the same height. They're never going to be exactly the same height, but they're all about the same height. So how do we describe the center of the graph? So that was the shape of the graph. So roughly symmetric. skewed to the right or skewed to the left. So the next thing we're going to talk about is describing the center. Now, please make sure when you're describing the center, you're talking about the center of the distribution. Don't just say the center is. Specifically, what are we looking at? We're not just looking at the center of the data, we're looking at the center of the distribution. Okay, so with a roughly symmetric graph, remember nothing in the real world is going to be perfectly symmetric. So we're always going to say it's approximately symmetric. Where exactly is the center or the middle of that graph? If we were to graph it, so something that's roughly symmetrical, the mean and median are going to be about the same. Okay, so let's look at this graph. The mean is the average. Since it's symmetric, there's going to be as many low as there are high, so the average is going to be in the middle. The median, remember, is the exact middle point of the graph. It's going to be also somewhere in the middle because there's equally points as high as equally points as low. So the mean and the median can describe the center of a roughly symmetric graph. What happens if it's right or left skewed? For graphs that are right and left skewed, you want to use the median. We're going to explain why later in the section, okay? But when you're describing the center, please make sure you state, since the graph is left skewed or right skewed, we're going to use the median to measure the center of the distribution. Just a quick reasoning, so if you think about this, this graph is skewed to the left because there's a long left tail. Okay, the median is going to be, if I was to line these dots up, the actual middle of the graph. The mean, okay, is the average. This tail is actually going to pull that average down a little bit. Okay, so the mean is going to make the average or the middle look like it's lower than it actually is. Okay, so what exactly are spread and outliers? We're going to learn more about the outliers and the spread in later sections, but for now we're just going to get a general idea of what spread is. Okay, so we have the shape, the center, and the spread and outliers. Okay, so spread is basically looking at how spread out or varied the data is. This is going to be a word we're going to be using often. Varied, if it's variable, that means there's a huge difference between the lowest and the highest. If it's not varied, then there's not a huge difference between the lowest and the highest. So let's just take a look at an example of the sum of the rolls of the dice vary from 2 to 12. Okay, so we're talking about the spread of the data. Okay, we're just stating what is the spread. The sum of the rolls of the die vary from 2 to 12. In this case, we're not saying that it is varied or is not varied. We're just specifically stating what is essentially the range of the data. Okay. With outliers, we'll formally define this in later sections, but for now, we're just going to look for anything that's outside the normal data range. So if we're taking a look at household size in South Africa, if we look at this data, we can see most of the data lies between maybe 3 and 12. Okay. However, there's these 2 points at 15 and 26 that are far away from the rest of the points. So we can say that it appears that there are 2 outliers of household size 15 and 26. Okay, so if we take a look at this distribution, the below dot plot is the reported findings of how many people are living in a household in South Africa. Okay, so we have household size, and we know it's South Africa. So if we said describe the distribution, take a minute and think about what that's going to look like before I go through the answers. I gave you the first one just to show you what I mean by in context. So when it says describe the distribution, you have to know that means SOX. Shape, outliers, center, and spread. Okay, so S, notice how this is in context. The shape of the distribution, okay, specifically that word distribution, for household size in South Africa is skewed to the right and unimodal. Okay, so it's skewed to the right, so we got a long right tail here. If I was going to draw a curve over it, unimodal, there's only one mode. Okay, so take a minute and think about how you'd answer those. Pause the recording, and then I'll go over them. All right, let's see how you did. Okay, so just remember that you know that that's SOX, and one of the other key things is that it's in context. If it's not in context, you will get points taken off, so keep that in mind. Okay, so S was our shape, O is our outliers. So in the previous slide, we said there appears to be 2 outliers in the tail of the distribution, those who reported living in households of 15 and 26 people. Notice, in context, households of 15 and 26. C is the center. Since it's skewed to the right, we have a long right tail, we want to use the median or the midpoint. So notice how we specifically stated we're using the midpoint or the median. The midpoint of the number of people living in the households is about 6 people. Okay, so if you really wanted to, you could count and then count, 12 on either side. Okay, and the spread is talking about how varied the data is. The household size for South Africa, there's your context, vary from 3 to 26 people. In this case, we're just talking about the range. Okay, in later cases, we won't be using the range, but this, like I said, this is just a general overview of it. Okay, so why do we display our distributions in dot plots or histograms? The whole goal of doing this is to compare distributions. So some of the most interesting statistics questions involve comparing 2 or more groups. So when you are asked to compare 2 distributions, you want to still use your SOC. So we still want to discuss our shape, our center, our spread, and the possible outliers whenever we're comparing distributions of quantitative variable. A key here is to use comparative language. All right, so if we decide, hey, let's take a look at household size in the UK versus South Africa, and I asked you to compare the distributions of household size for the 2 countries, you want to use your SOCs. You have to understand that you're going to use SOCs. The key is context and using comparative language. Make sure that you state, using comparative language means stating that one is higher or lower, one is skewed to the right while the other is skewed to the left. So put both distributions in the same sentence. So go ahead, take a second, try this, okay, using comparative language, and then check your answer on the next slide. Okay, so what's key? We sort of already talked about this. It is imperative that when you compare data, you cannot just describe each distribution separately. Don't give me 8 sentences, 1 for South Africa and 1 for the UK. You have to make it 1 paragraph, essentially with 4 sentences. You must use comparative language such as greater than, less than, or about the same. You will not get credit on the AP exam if you don't. Below, when I describe and compare the 2 distributions, the red words are going to be your comparative language. So what's the shape? The distribution household for size UK samples is roughly symmetric and unimodal. Now notice, while the distribution for South Africa is skewed to the right and unimodal. Okay, if it was the same, you would say is the same as. The center, okay, household sizes for South Africa students tended to be larger than UK students. The midpoints, and then specifically state what the median or the midpoints are. The midpoints of the household sizes are 6 people and 4 people respectively. You could also put that in 1 sentence. Household sizes for South Africa. The median household size for South Africa is about 6, which is larger than the median household size in the UK, which is about 4. Okay, so what's the spread? How varied are there? Okay, the household sizes for South Africa vary more. What do they vary from? 3 to 26, which is different than the UK, which vary from 2 to 6. Notice, once again, it says vary more. Okay, that's 1 sentence that's comparing the 2. Once again, the outliers. There don't appear to be any outliers in the UK distribution. However, okay, because there's nobody out here, the South African distribution seems to have 2 outliers in the tail of the distribution. Okay, students who reported living in households with 15 and 26. So you can't specifically say, or you could say they both have outliers. One has an outlier while the other does not. Okay, you're using that comparative language. So get your English class in class. All right, so stem and leaf plots, you've seen this before. This is just a quick review. This is just a simple graphical display for small data sets. So I would not use stem and leaf plots for large data sets. It takes too much Okay, so just to refresh your memory from your stem and leaf plots that you've done in the past, the data below represents responses of 20 female AP statistics students' answers to the question, how many pairs of shoes do you have? Take a minute, construct a stem plot. So this is the number of shoes. Okay, see what your answer is and just check and make sure that you've done it correctly. But don't forget to include keys and labels. If you don't include a key or a label, it will be marked incorrect. Okay, so did you use the stems as 1, 2, 3, 4, and 5? Okay, so we have 13, 26, 31, 49, and 51. So we know we have 1, 2, 3, 4, 5. Okay, add our leaves. So remember 1, 9 means 19, 1, 3 means 13, 1, 3 means 13. Make sure you order them. Okay, so make sure that they're going from the smallest to the largest, so 3, 3, 5, 9 instead of 9, 3, 3, 5. Okay, and then make sure you add a key. So make sure it doesn't matter which one you use. So 4, 9 represents a female student who has 49 pairs of shoes. You will get a point taken off if you don't include that key, so make sure you do, please. Okay, so oftentimes we will split stem and leaf plots or make back-to-back stem plots. So when data values are bunched up, so if there's a whole bunch of values, you know, in the 10s, so there's like from 10 to 15, there's 32 values. Instead of making a super long leaf, okay, we want to, maybe we want to split that up. So that's one reason that we make split stems. Or if we want to make back-to-back stem plots, we do that when we have two distributions, here's the key thing, of the same quantitative variable that can be compared using back-to-back stem plots. Okay, so now let's just say we wanted to take a look at the number of shoes that females owned versus the number of shoes that males owned. Okay, so split stems means, notice right here, there's 2 zeros, 2 1s, 2 2s, 3 2 3s, 2 4s, and 2 5s, just so we don't have huge leaves. Okay, we put our stems in the middle, and then on the edges, we put our leaves. Okay, and notice the labels, females, males. Okay, so it's easy to look at the distribution. It's easy to see that, hey, females own a lot more pairs of shoes than males do. And then once again, please make sure that you include the key. Okay, so histograms. You're going to be working with histograms from now till the end of the course. So get used to them, get good at them, make sure you know how to do them on your calculator, draw them, label them. So quantitative variables often take on many values. So sometimes a stem and leaf plot or a dot plot is just not realistic. It's too hard to graph, takes too long. So a graph of the distribution may be clearer if nearby values are grouped together. The most common graph of the distribution of one quantitative variable is a histogram. So hopefully you looked at the article from the Forbes article that took a look at what is the difference between a histogram and a bar graph. So you should understand the difference between those two. Bar graph, remember, is for qualitative or categorical data. Quantitative is a histogram. So how exactly do we make a histogram? Number one, make sure you divide the range of data into classes of equal width. Okay, so all of your bins have to be the same width with the histogram. The area is determined by the height of all of the classes are fairly represented. So that just means that you don't want one bin wider than the other, so that would sort of skew the distribution. It's not going to look correct. Okay, find the count, which is either your frequency or your percent, which remember is relative frequency, of individuals in each class. So if you decide that you have a class from 0 to 5, how many people fit in that category? Label and scale your axis. Okay, so make sure that you label your horizontal axis with numbers and in context. Label your vertical axis. Also label it with numbers. The height of a bar equals its frequency. Okay, so if there are 5 people in that category, make sure your bar goes up to 5. Adjacent bars should touch. There should be no spaces with a histogram. If there is a space, that tells us that that specific class contains no individuals. Okay, so a space means there is no one in that class. Okay, where a space in a bar graph doesn't necessarily mean that. People always ask, how do I know how big to make my classes? There's no one right choice for the class, okay? If you choose too few of classes, it's just going to look like a giant skyscraper and you're going to have no idea what the distribution actually looks like. But if you have too many, it's going to be too complicated and not give too good a picture. So on your graphing calculator, go in and you're just going to have to mess with the class widths until you find one that you like. Okay, so what I would like you to do is take a minute and make the histogram on just a piece of paper. So the table below represents data on the percent of residents from each state who were born outside of the U.S. Okay, so when this says class 0 to 5, that means 0 to less than 5% of residents were born outside the U.S., 5 to 10% were born outside the U.S., 10 to 15% were born outside the U.S., okay? Now the count tells us how many people, okay, how many states had a percent of 0 to 5 who were born outside the U.S. So here, 20 states have between 0 and 5% of people who were born outside the U.S. 13 states have between 5 and 10% of people that were born outside the U.S. Okay, notice our total is 50 since we have 50 states. Go ahead, make a histogram, and then you can check your answers. Okay, so once again, labels, percent of foreign-born residents, numbers 0 to 5, 5 to 10, 10 to 15, number of states labeled in context and numerically. All right, our class is our percent of foreign-born residents, and the number of states is the count. So from 0 to 5, there are 20 states that had between 0 and 5% that were born outside the United States. Okay, so what is the difference between a frequency versus a relative frequency? So remember, a relative frequency is your percents. Okay, so if we wanted to look, remember from 0 to 5, there were 20 states that had 0 to 5% that were born outside the United States. So how did we get that percent of 40? We just took 20 divided by 50 to get 40%. So a relative frequency histogram, okay, is going to show you the percent of people. Okay, so 20% of the states had between 0 and 5% born outside the U.S. That's a tongue twister. Okay, so just keep in mind though that the percents then have to add up to 100. So relative frequency histograms are sometimes more useful than frequency histograms because we can compare two distributions, especially when the number of individuals is different. So let's just say we are comparing two countries, okay, and we are comparing the percent of people that were born outside of the United States versus the percent of people that were born outside of Canada. All right, if we're looking at Canada versus the U.S., if we just looked at frequency counts, the population in both are different, so it's not going to give us a good comparison or distribution. But if we compare the percents, okay, it's sort of standardizing the data and making it in one unit. Okay, so how is a relative frequency graph different? It compares the percent in each class to the total. The bars represent the percent that fall within each class. Please make sure, here are 4 tips that you need to make sure you understand. Please don't confuse histograms and bar graphs. Histograms resemble bar graphs, but their details are different. A histogram is for a quantitative variable. The horizontal axis of a histogram is marked in the units of measurement for the variable, versus a bar graph is the distribution of a categorical variable, or to compare the sizes of different quantities. In this case, the horizontal axis of a bar graph is the categories or quantities being measured. When you draw a bar graph, you include blank spaces in between the bars. For histograms, there are no spaces. So for example here, the space between 20 and 25 means there is 0. Okay, so please just make sure you understand the difference. Okay, please make sure that you don't use counts in a frequency table or percents in a relative frequency table as data. Okay, as the data. So below is a frequency table. So here's our frequency table displaying the lengths or the number of letters of the first 100 words in a journal article to display the data. Can we see what Billy, who created these, did wrong? He used the counts as the data when drawing the histogram. So what he did is he said there were 2 counts of 1, 2 counts between 3 and 5, and so on. So please just be careful. Make sure that you use percents instead of counts on the vertical axis when comparing distributions with different numbers or observations. Okay, so if we want to compare 2 distributions and they're in different units, use the percent as your vertical axis. Okay, so let's say that Mary was interested in comparing the reading levels of a medical journal and an airline's in-flight magazine. She counted the number of letters in the first 200 words of an article in the medical journal and the first 100 words of an article in an airline magazine. She then used Minitab, which is a statistical software program, to produce the 2 histograms. Okay, histogram A and histogram B. So what do each tell us? If you take a look at histogram A, it's misleading. It compares the frequencies. However, the problem was the 2 samples had different sizes. The first one had size 100 and the second one had size 200. The first one has size 200, the second one has size 100. So using the same data, Mary's teacher produced the histograms in figure B. If you take a look at figure B, we're now comparing the percents. Okay, so by using relative frequencies or percents, we can provide an accurate comparison of word lengths in the 2 samples. Okay, because we're talking about the word length of 2, what percent had a word length of 2 in the medical journal versus what percent had a length of 2 in the airline journal. Okay, we're here, this is the count. How many had length of 2? How many had length of 2? Well, obviously one of them is going to be less because we only looked at 100 words instead of 200 words. Okay, make sure your graph is meaningful. Just because you have a graph that looks nice, it's not necessarily meaningful. All right, the graph below represents the students in a small statistics class recorded the number of letters in their first names. One student entered the data into an Excel spreadsheet and then used Excel's chart maker to present. Okay, so here's just a few last cautions and common mistakes that students make when making histograms. 1, don't confuse histograms and bar charts. Okay, so those few things we talked about, make sure you understand the differences between the 2. Don't use counts in a frequency table or percents in a relative frequency table as data. This one you don't really need to worry about. I've never really had any students that have any problems with that. Use percents instead of counts on the vertical axis when you're comparing distributions because it puts it in the same units. Okay, just because a graph looks pretty, it doesn't necessarily mean that it's meaningful. So make sure your graph is displaying meaningful information that someone would actually use. Okay, so just a quick thing about histograms in the calculator. For this course, we will be providing video instructions and PDF instructions on how to use both the TI-84 and 89. Make sure you take a look at them on Blackboard. If you would like to know how to create a histogram on Blackboard, or a histogram on your calculator, please go to Blackboard, go to the calculator instructions, and there's where you'll find instructions on how to create a histogram on your calculator. Please make sure you do this as you will be using this throughout the entire course.